Several capacitors can be connected together, and these connections of capacitors behave as a single equivalent capacitor. The total capacitance of this equivalent capacitor depends both the individual capacitors and the way how they are connected to each other. There are two basic combinations, and they are called series combinations and parallel combinations of capacitors. Okay, first let's start with series combinations. In the figure, you can see that there are three capacitors arranged in a row, and this type of combination is called series combination of capacitors. As you can see, that this combination is connected to some external constant voltage source. Then what this source do, it takes some charge from the first plate of the first capacitor to the second plate of the third capacitor. Then the first plate of the first capacitor becomes positively charged, and the second plate of the third capacitor becomes negatively charged. After that, charges are induced on the other plates of capacitors. So for example, the second plate of the first capacitor becomes negatively charged, minus Q, and this one becomes positively charged, negatively charged, and positively charged. Now, as you can see, the plates of each capacitor has positive and negative charges respectively, right? So that's why the charges on each capacitor, they are equal to each other. We can write it as, well, Q1 equals Q2, and it is also the same as Q3. Even though the charges are same on each capacitor, the potential drop in each capacitor, they are different because they have different capacitance, right? So now let's find them. For example, the potential drop on the first capacitor, let's denote it with the letter U1. It's just Q1 divided by the capacitance C1. U2 is Q2 divided by C2, and U3, it is Q3 divided by C3. As we have said, that this combination of capacitors behave as a single capacitor. So as you can see in the second figure, that the capacitance of this equivalent single capacitor is Cs, okay? And this battery, for example, this constant voltage source could be battery, takes some charge from one plate to the other. So that's why on the one plate there is a charge Q, and on the other there is a charge minus Q. So you see, the total charge is also the same as Q1, Q2, and Q3. So that's why we can write Q total charge is the same as Q1, and it is also the same as Q2, and it's also the same as Q3. We have already determined the potential drops in each capacitor. So the total voltage U is the sum of U1, U2, and U3. Entering expressions for U, U1, U2, and U3, we get the following. So the total voltage is the total charge divided by the total capacitance, right? So it is Q divided by CS. Then it is Q divided by C1 plus Q divided by C2 plus Q divided by C3. Canceling Q, we get the following expression. Reciprocal of the total capacitance is the sum of reciprocals of individual capacitances, right? So it is reciprocal of the first capacitor plus reciprocal of the second capacitor and plus reciprocal of the third capacitor, third capacitance. If we have more than 3 capacitors connected in series, then the answer will be very similar to the expressions we have found above. So it is just 1 over CS equals 1 over C1 plus 1 over C2 plus 1 over C3 plus 1 over Cn.